so far we had seen how we understand this. We'd also understood how we understand this and this. And so what's left over is understanding where this comes from and where this comes from. By the way, here, if you remember, the key aspect to understanding this experiment was what? Yeah, the critical current. But what was important about the wave function to explain how come the response to field was this? Yeah, I think I heard it. So you needed a sign change in the superconducting order parameter, right? So the sign change let you get this increase in field. Right. And so we're focusing a little bit on these sign changes. And the other thing I wanted to emphasize, which is actually critical and worth emphasizing, is that to get a superconducting instability, you need to have these two symmetries, either inversion symmetry or time reversal symmetry. If you break both those symmetries, it's very unlikely that you'll get a superconducting state. So if you break them strongly, it's highly unlikely you'll get a superconducting state. And I think all superconductors exist have one of these two symmetries in 3 dimensions. I won't go into detail, but in 2 dimensions there's additional symmetries that allow you to have a degeneracy between all k and minus k, and those additional symmetries play roles in some interesting materials. For example, in Ising superconductors, they has one of these additional symmetries that lets you get a strong superconducting state in a finite magnetic field. All right. But let's move on from here. All right, so I described Cooper pairing amongst the degenerate states you get when you have both time reversal and inversion symmetry, which you can call a spin up and spin down at a particular k. So here's pairing between k up and minus k down, for example. And then spin triplet would be pairing between, say, k up and minus k up, and then k down and minus k down, and also there's a spin triplet combination which is up down plus down up, and that's this dz component. And so these wave functions had to be odd under k goes to minus k, and these wave functions had to be even. All right. Okay, and so what we were turning to now was we'd understood in some sense what time reversal and inversion symmetry do. We're turning to what the other symmetries in all our crystals imply for Cooper pairing. Okay. And so I showed you this character table, and the one thing I want to point out is that throughout this field we always use pictures, and we say things like kx squared minus ky squared to describe superconductivity, but none of those pictures should be taken seriously. The only thing that really dictates our symmetries are these group representations, right? And so these are always sort of pictures of describing these particular types of group representations. And that's important to remember in some cases, because there are cases where people do take these kinds of pairing symmetries literally. Okay. All right, and so I showed you some examples, and I think we ended up right here. In particular, I was pointing out this relative phase factor of I that said that this particular spin singlet wave function carries angular momentum, and because it carries angular momentum, it breaks time reversal symmetry. And I said that the polar Kerr effect seen in such materials is a consequence of this broken time reversal symmetry. And I'm not going to say much more about that, but just leave that there. And now let's go on from where we were. So now, so in this slide I showed you, for example, we describe the wave function by this kx squared minus ky squared would be a typical dependence showing the behavior of the gap around the Fermi surface. And traditionally in this field then, we look at our group, and this is the same group I showed before with the same representations, but now I've labeled even and odd parity. And what we do is we write down corresponding psi of k's and d of k's that correspond to those symmetries. So these are, again, this shorthand notation I'm telling you about, but it helps us to understand what the states look like. But everything is simply defined by the group theory itself. And so some typical choices are A1G. We say psi of k is 1. That just means we have a constant gap around the whole Fermi surface. Here is the d wave state that I mentioned before, kx squared minus ky squared, and that was the picture I showed you on the previous slide. Here is this EG state, which has this kz, kx, and kz, ky, and in the previous slide I put a factor of I between these two. What's interesting with this state is because this has symmetries of a square, you actually have two degenerate states that you can form any linear combination of to form your Cooper pair. And these two degenerate states means you have 2 degrees of freedom. And now you can begin to understand how you might get multiple superconducting phases, because now we have 2 superconducting degrees of freedom. And indeed, the fact that we have these 2 degrees of freedom can give us multiple phases, and that's what's happening in uranium platinum 3. We belong in one of these so-called higher dimensional representations, and we choose linear combinations corresponding to, well, how you choose the appropriate linear combination is a question I won't answer here, but you can answer within a Ginzburg-Landau type theory. Right. Okay. Now here, like I said, I'm not going to talk too much about the spin triplet states, but the one thing I want you to notice is, again, this is a D of K. It's a vector. It has components X and Y in this case. And then it's always got some linear momentum dependence here, meaning it's odd under K goes to minus K, right? So here, X at Kx, K goes to minus K, Kx goes to minus Kx. And so you can see these are all odd parity. These are all even parity. These are all K squared. Yeah, and we'll, in a little bit, go from these particular representations to actual observable quantities like gap measurements. Okay, so let's do that now. I've told you about kinds of superconducting pairing. I've hinted at the fact that we're going to talk about low energy excitations, but I haven't told you how we calculate the low energy excitations. And so now we're moving into more current theory. Okay, this is really from the 1990s largely, and this is our understanding of the 1990s. But the picture is the following. So I've introduced my normal state before. I told you the key point to remember is that at each momentum point we have a 2 degenerate states, a spin up and a spin down. Right? And so what I want to do now is also, in my theory, introduce superconductivity. And so here's the superconductivity I talked about in the previous couple slides, the even and the odd parity states. But the key point to get in the excitation spectrum is to study this Bogoliubov-Desgen Hamiltonian. So this results from a mean field theory of superconductivity. So we ignore fluctuations, but this mean field theory gives us a lot of information. So just look at the structure of this. Right here, this is our normal state. And these are, again, 2 by 2 matrices corresponding to the single band picture. I showed you those 2 by 2 matrices before. So again, up, down, minus, down, up would be the spin singlet case. But notice that here, this is multiplied by an identity Pauli matrix. So this is a 2 by 2 identity matrix. It's an identity matrix because we have this exact degeneracy between spin up and spin down. They have to have the same dispersion. That's why they have the same Fermi surface. So I have an identity matrix here and another identity matrix here. What superconductivity does is it formally couples electrons and holes. Right? So this is the hole part of the Hamiltonian, this is the electron part of the Hamiltonian, and here's the pairing. And if we look at the form of this, we can see that when this energy and this energy are the same, the coupling between them is going to be the strongest. This energy and this energy are the same on the Fermi surface, and that's when the coupling is biggest. And so what this is describing is we have an electron band, which you can imagine comes parabolic like this, and a hole band, which is parabolic like this. And where they meet at the chemical potential, at the Fermi surface, you gap them, and you get this superconducting gap. And we saw some pictures of how you might measure that in ARPES in the last talk. Right. And one important feature in this Hamiltonian, which plays a central role in all topological arguments that we're interested in today, is that this Hamiltonian has a built-in charge conjugation symmetry. So in particular, you can see maybe qualitatively that if I flip the electron and the hole, so I've interchanged those two, I have some sort of symmetry in the Hamiltonian. And more specifically, this is the symmetry here. And what I thought I would do is just show you explicitly how this formula actually pans out when I use it on the board over here. Because it is, like I said, if you want to have a Majorana particle, you do need to have this charge conjugation symmetry built into your Hamiltonian. And so it plays a central role in why superconductors are interesting for these Majoranas. So let's just go through that exercise and see how we get this charge conjugation symmetry as a general property. All right. So I've started it here already. I have my charge conjugation operator. It does 2 things. I'm just telling you it does these 2 things. It takes k to minus k. It's also an anti-unitary operator. So because it's anti-unitary, you have to have a complex conjugate operation joining its principles. So this tau x, this is a Pauli matrix that looks like this in particle hole space, which means it's going to change the electron and the hole parts. All right, so that's what tau x does. And this Hamiltonian here is that Hamiltonian that I've written HBDG but at minus k. So let me just look at how this performs. So I have a complex conjugation operator, so I'm going to take that through here, take the complex conjugation of this Hamiltonian at minus k, and this is a real matrix, and so I can square that complex conjugation operator here, and that gives me 1. Right? And so I'm going to get something that looks like this, tau x h complex conjugate of minus k tau x after I take care of that. And now I'm just going to write this out. I'll write this. So here I'm going to drop the Pauli matrices that I had up there and take All right, so here I've taken k to minus k. In the materials when I have both time reversal and inversion symmetry, the dispersion for k and minus k is always the same. So I've just dropped the k index here. It's the same for k and minus k. So I can actually keep this as k. But for superconductivity, this minus k will play an important role. So you can see the complex conjugate of the normal part, this is a real number, so it does nothing. But the superconducting gap can be complex. I showed you that example where I had that I between the two components. And so you have to worry about that here. So this is after carrying through this complex conjugation operator. Now I just have to multiply these three 2x2 matrices together. And when I do that, I get the following. And you can check. So this is what I get after I perform the charge conjugation operator. Now look at what I wrote down in the terms of the symmetry here on the PowerPoint. I picked up I should have put this minus sign here. I pick up a minus sign, I've flipped this k already. So this should be minus h of k. But notice that this thing doesn't look quite the same as my original BDG Hamiltonian up to an overall minus sign. In particular, I have this delta transpose of minus k as opposed to this delta of k. So does anyone know what physical ingredient I'm missing here to go from this delta transpose of minus k to minus delta of k so I can finish this derivation? I've already hinted at it. It's an important principle for all Cooper pairs. Say again? Yep, Pauli exclusion, exactly. Pauli exclusion says that the Cooper pair has to be anti-symmetric if I interchange the two. The anti-symmetry is captured by taking the transpose and sending k to minus k. That's not entirely obvious from what I wrote earlier. I just told you that, but that is exactly what happens. So this becomes indeed what we see here. And so in many of the theory papers you read about this is a starting step to write down this symmetry transformation, and we say we use it. It's sometimes useful even for experimental colleagues to understand exactly how we get that. And so I think it's and like I said, it's actually a very important symmetry in the context of superconductivity. Okay, so I've identified three symmetries that are important: time reversal, inversion, and now charge conjugation. And so let's go on and let's see how we diagonalize this Hamiltonian to find the excitation spectrum, because that'll tell us about the notes. All right, so here I've written down that BDG Hamiltonian. It turns out you can diagonalize this exactly both for the spin singlet and for the spin triplet cases. And the form of the two solutions is very similar. We get this normal state term squared plus the psi of k squared. Or we get this normal state squared plus the magnitude of d, which this is the dot product d dot d star. So here we can identify this as the square of some gap. It's now a positive quantity, so we don't have to worry about these negative gaps. And here we turn this vector quantity into a scalar. This is d dot d star. So we also have a gap for the spin triplet case. So in both cases we have a gap. I'll make a little point here. I've assumed something that may look strange to you. I've said let's assume this d cross d star is 0. in most cases of interest, this is always true, but it turns out that it may be the case in uranium tellurium 2 that this is not true, and so we have to start worrying about this. But all it does is introduces a second gap to the problem, so it doesn't really change any of the physics I'm going to talk about now. All right. So what we're after, what we want to understand are there zeros, and what kind of zeros can we get in a superconductor? To get zeros, then we need the excitation energy to be 0. So we're looking for E of k to be 0, and we see generically this excitation energy is given by the sum of two squares, this squared plus this squared. So let's understand what that means. This first term squared, well, this simply means we have some momentum on the Fermi surface. So we're sitting on the Fermi surface, and that tells us our zeros will lie on the Fermi surface. The second term, the gap being squared, well, this will only vanish when psi of k vanishes. And you may have seen this, and I didn't emphasize it, but there's two ways psi of k seem to vanish generically from the group theory arguments. It either vanishes in a two-dimensional plane or it vanishes along a line, right? And so we can imagine what happens if we have this vanishing along a line in momentum space, and we imagine we have a three-dimensional spherical surface, then that line's going to intersect that sphere at points, and we'll get point nodes. The other possibility is that this psi of k vanishes in a plane, and if we have a plane, it intersects a spherical Fermi surface along a line, and we get line nodes. And looking at this theory, we see these are the only possibilities we would expect. We either get point nodes or line nodes. And so in the next slide I'll talk about the difference between those. So I'll give an example and I'll talk about the difference experimentally between those two. But I should make a caveat. I've been considering here a single band the whole time. In practice, all condensed matter materials are multiple bands. And in fact, multiple bands in general will change this conclusion, and I'll give you a chance to give a feeling for how you can see how this change happens when we talk about a topological analysis for the appearance of these nodes. But I won't go into details on that, I'll just give you an overview and a flavor. All right, so you can actually get Fermi surfaces as well, but not in this picture here. And you can only get Fermi surfaces for the even parity case, not for the odd parity case. All right, so that's the change you get when you do a more general analysis than the single band theory. Okay, so just to drive this point home, let's look at an example I showed you before, one of the more complicated spin singlet examples. So here is my excitation energy that I want to set to 0. I'm going to imagine that I have a spherical Fermi surface. So this is satisfied on a sphere, and that's this gray sphere here. And then I'm going to take as an example this psi of k, which is this kz, kx plus I, ky. Right? And now in the theory, I need to take the magnitude of this squared, and I take the magnitude of that squared, I just get kz squared times kx squared plus ky squared. And we can now look for zeros in this now. We can see that we get a 0 when kx equals ky equals 0. That defines the kz axis. And so the kz axis goes through the sphere at 2 points. And so we get a point node here and a point node here. And we can also get zeros when kz equals 0. That gives the xy plane. And in the xy plane, that intersects the sphere along this line in the basal plane, and we get this line node here. So this example has both point nodes and line nodes. All right, so I've emphasized this point before, and I'm going to emphasize it again. We always draw these pictures of wave functions like kx squared minus ky squared, and it's easy to see when I have this kx squared minus ky squared how to get nodes, because I just set that object to 0. But actually, I tell you that the structure of nodes is not given by that, but by the group theory itself, meaning it's defined by these representation tables. And so I thought it'd be useful for you to understand how you might show that in a general sense as opposed to looking at specific examples. All right, and so here I'm going to focus again on this D wave case here. Right. So here I have the spin singlet order, and as a picture I call this psi 0 kx squared minus ky squared. Other people write this as cos kx minus cos ky, so you do get different representations. And now I'm going to imagine, I'm going to try to understand how these ones, ones, minus ones give me nodes necessarily in my wave function. So in particular here, I see that I get some minus ones, and it turns out these minus ones are what dictate the existence of nodes. So here as an example then, I imagine simply in 2 dimensions, I have some scalar wave function kx, ky, so some spin singlet state kx, ky that only exists as a function of kx and ky. All right, and now what I'm going to apply is this twofold rotation symmetry here. That's this symmetry here. It interchanges kx and ky. So these two get interchanged. And so I've written out explicitly kx to ky. And because this is a spin singlet Cooper pair, spin singlet is unchanged under any rotation. The spin structure of this does not change. That's going to be, oh, sorry.
Projector likes to take a minute to come back.
Okay, well, but the key point is that you might worry about the spin structure of the Cooper pair being affected by the rotation. For the spin singlet, it is not, but for a spin triplet, it is. And so the argument I'm giving here for spin triplet needs to be somewhat changed. But for the spin singlet case, this is correct. And so we only worry about the transformation of the momentum variables. And so I had this kx, ky. It got interchanged to ky, kx. And I think for the next part, I actually do need the slide to go ahead with. But so it's just going to warm up. Okay, I see it flashing. All right.
It's the classroom, so it automatically shuts off after something like that.
Let's see. All right, so I should mention, if you're interested, this argument was first given by Gorkov and Volovic in 1987 in one of their early papers on the development of this theory for superconductivity. Oh good, we're back. Perfect. All right, so here, because of this transformation property, I know this twofold rotation must imply a sign change in the wave function. Right, so this must go to minus itself. And so I impose that here. I get psi ky kx, the twofold transformation interchanges the two momentum variables, interchanges kx and ky, but under group transformation I pick up an overall minus sign. Now, you can see what happens here. If I take kx and ky to be equal, so these are the same, then I have psi kk equals minus psi kk. I take one to the other side, I get 2 psi kk equals 0. And so just from this alone, I know the node must be there. So if you're looking at group tables, you can apply the transformation property to your wave function, and you can also use the definition on the group table to tell you that these minus ones dictate nodes in the superconducting wave function. So this is why the nodes are there for every particular example we have of a D-wave state, because it follows just from the structure alone. Okay, so with that note, let me just talk about the experimental properties. This was meant to come in afterwards, but okay.
Maybe you're not running the presentation.
Oh, yeah. Sorry, had a question?
So does the other minus sign on that representation give you the other type of node then? One gives you point nodes, one gives you one node?
No, it's not so simple. And you do need to do these spatial, you do need to look at the transformation of the momenta. So I purposely did not choose this minus 1 because that takes kx, ky to ky minus kx. And so you have to be a little bit more careful with that, because now I have a ky and a minus kx, and I'm going to have a kx, ky here, so I have to be careful how I structure it. So it's not so simple. The point nodes often come into the spin triplet case because you have a more complicated transformation property because of the spin triplet nature of the wave function. And so you just have to play with these for a while, and this is really the simplest example. Yes? Yeah?
Does spin orbit coupling often have any link in determining whether it's point or line nodes? As you turn it on, does it turn?
Yes, yeah. So indeed. So it's not that critical for the spin singlet case because the spin leaves the structure. But in the spin triplet case, if you have no spin orbit coupling, then you can ignore the spin part completely, and you can do a treatment like this to determine nodes. So you can treat the spin and the orbit separately, right? Yeah.
So when applying the symmetry transformations, do you have to start at kx, ky, or could you start somewhere else along that plane?
Oh, this is any kx, ky, right? So this is any kx, ky, yeah. Yeah, this is general. I mean, the only thing I missed is I didn't add a KZ to this, but in this argument, KZ just follows along as a dummy argument, doesn't do anything.
Okay.
Actually, that's not true. For this twofold rotation, KZ changes sign, so I have to be careful with that. But, okay, but yeah, so this explains the Coop rates. Yeah. But my main point here was just to say that these group tables are what define the nodes, not the particular pictures that we show like this. These come from this. And so you have to remember that when you're looking at these. And so you do get artificial nodes in some problems that are truly artificial. All right. Okay, well, I can tell you what's missing here. So what does it mean that we have nodes? Well, nodes are actually fairly easy to see experimentally in the sense that at very low temperatures, we don't get this exponentially Boltzmann-like suppression with a gap, no minus delta over kBt, but instead we get power law dependencies. And so, for example, if we look at specific heat, if we have line nodes, we get T squared. If we have point nodes, you can't see it, but this is T cubed. I showed you, I mentioned an example of the London penetration depth. That's how far the magnetic field penetrates inside the superconductor in the Meissner state. If we have line nodes, that goes as T. If we have point nodes, that goes as T squared. Ignore what's in the brackets here for now. And then you can also see differences in other behavior in 1 over T1. At low temperatures, there's a T cubed or T fifth dependence. And in heat conductivity, there's a T squared or TQ dependence. And so that explains this behavior I showed you in this yttrium platinum bismuth. Here's a conventional, conventional S-wave type superconductor. Okay, at least in terms of excitation spectrum, this has a full gap. But here you see this kind of linear in T dependence, suggesting that there are line nodes in this material. And so I think we only have to, I think we've explained all the missing experiments so far. All right, so that's what I wanted to say about nodes. They're dictated by symmetry. And they have experimental consequences. And that kind of gives us the picture of superconductivity into the 1990s. But then more recently, people have introduced topology in understanding things. And so now what I'm turning to is a quick overview of what happens when we consider topology. And the motivation, again, is going to come from nodes. And so here's some ARPES measurements on this potassium iron 2 arsenic 2, and they're looking around the gamma point. All right, so here there's Fermi surfaces around the gamma point. Just to give you a quick overview for these iron-based superconductors, you typically have hole pockets here, electron pockets here, and often you have a repulsive interaction for Cooper pairing between this and this, which means that the gap function is usually positive on this side and negative on this side. And notice if I sum the gap function over all k, I'll satisfy that condition that that equals 0, meaning that electron-electron interactions can drive such a state. But here it's simply a plus and a minus that accounts for that overall 0. However, in some of these materials, in particular this one here, you do find actual nodes on these Fermi surfaces. And here's a picture coming from ARPES measurements on the, around the gamma point. And what they found was very interesting. They found that in this material, they didn't have just 4 nodes that you might expect from a D-wave state, but instead you had 8 nodes. And the only way to understand 8 nodes is if the gap goes from plus to minus to plus to minus to plus to minus. But if you look at these two pictures, remember in the D-wave state, if I did a 4-fold rotation around here, the minus goes to plus, I pick up an overall minus sign in my wave function. But here if I do a 4-fold rotation about this point, my plus goes to plus. And so formally this has the same symmetry as S-wave. And so often in the past these were called accidental nodes, and accidental nodes seem to occur quite frequently, and they're not classified by this analysis I gave you in the previous slide. And in fact, the only way to begin to understand these kinds of nodes is to go to a more general analysis, which is a topological analysis. And so I'm going to go to this topological analysis. This is perhaps the most complicated slide in this talk. But it's not so easy to, it's pretty easy to understand the final result. All right, so the idea is that if you want to understand nodes, you need to study the properties of Hamiltonians at a particular k point, because nodes sit at particular k points. And If you're familiar with real space arguments for topology, you might remember that there's a set of special symmetries that keep a real space point invariant, and those are time reversal, charge conjugation, and then the product of the two. And those three symmetries, or those two symmetries, are used to give a classification of all possible topological real space states. Well, you can do the same thing by looking at states that keep K invariant, and you can do a topological classification that actually maps directly to the so-called tenfold way that you see for real space arguments. But tenfold way means you have 10 types of superconducting classes with nodes, but in practice, superconductors place some constraints on that. What's important in this analysis is that we only keep the key superconducting symmetries, meaning we only require time reversal and inversion to exist. We can allow one of these to be broken or not, depending on the order, but these two have to be present because those are what stabilize the superconducting states. So any theory of superconductivity without these two symmetries is a little bit silly because you're not looking at stable states. In addition, all superconductors have this charge conjugation symmetry, and if my normal state has inversion symmetry, it turns out all superconductors have a net effective inversion symmetry. And what I mean by that is you saw that we get even and odd parity gap functions, and so even parity is clearly inversion invariant, but odd parity changes sign on inversion, so you say, well, hey, I don't have an inversion symmetry. But in a superconductor, we also have a gauge degree of freedom, and we can multiply that sign change in the inversion part by a pi gauge transformation to get a net effective symmetry. And so there is an effective inversion symmetry buried in the theory. All right, and so this limits the number of possible classes we have. I should mention the superconductor can break time reversal symmetry itself, even though the normal state has time reversal symmetry. All right, so this was this example where I showed you this kz, kx plus I, ky. That's the superconductor breaking time reversal, but the normal state maintains it. All right, so only below Tc do we have broken time reversal symmetry. All right, so you can in principle carry out a classification including these symmetries. And the symmetries that don't change k, well, one is time reversal times inversion. Time reversal takes k to minus k. Inversion takes minus k back to k. So this doesn't change k. It's also charge conjugation times inversion. Charge conjugation, as I pointed out before, takes k to minus k, and then inversion takes it back. And then you can look at the product of these two symmetries, and that gives you the so-called chiral symmetry that you saw before. All right, and so the way we understand this table is I've put these constraints in, and it turns out there's only 4 possible types of structures. So this says, okay, here I have a time reversal inversion that squares to -1, which must be the case if I have those, because that's what gives rise to the twofold symmetry of every state in every particle at each k. But here I assume that I have this charge conjugation symmetry, and I also have the product. Here I imagine that the superconductor breaks inversion symmetry, or breaks time reversal symmetry. So this is a superconductor that preserves time reversal symmetry. It's even parity. This is a superconductor that breaks time reversal symmetry. It's even parity. This is a superconductor that preserves time reversal but is odd parity, and this is a superconductor that breaks time reversal symmetry but is odd parity. So those are the 4 possibilities we get here. And we find that there's a few typical nodal structures that you get with these kinds of robust symmetries. We get the line nodes that we had before. So this would classify the line nodes we have in the dx squared minus y squared superconductor. So in 2 dimensions these were points, but if I take the 2-dimensional Fermi surface and extend it along the c-axis, those points become lines. And so that would classify that. And with topology, you get more information. You get an index. You find that these nodes are protected by some kind of topological index. And here we get an integer times 2. So any even integer protects these nodes. And there's a consequence to this index. This 2z means that these line nodes have associated with them certain surface states. And we saw a little bit about surface states in the last talk. These surface states in this particular case are known as flat band Andreev states. So at the surface you get a state that is k independent. And so if you're doing STM, because it's k independent, it's equivalent in all k, so you get a localized state. Right? And that comes from these line nodes here. If you break inversion symmetry, then you find that you no longer get if you break time reversal symmetry, you find that you no longer get line nodes, you can get point nodes. And I showed you point nodes corresponding to this in the previous slide. But you also get a surprise. You find you get the Fermi surfaces are in principle out topologically as well. And myself and some others have done some work in understanding these Fermi surfaces, and we know exactly how they appear in particular materials. But it is a surprise that you get these Bogdanov Fermi surfaces. But you can see this work is relatively recent. This is all 2017. And so we're getting to some fairly modern studies of these superconductors. In the odd parity case, we find that if we have an odd parity superconductor that preserves time reversal, we don't expect to see any nodes. So there's no topologically protected nodes there. But if we have a odd parity superconductor that breaks time reversal symmetry, then we expect to see that we can get point nodes that are protected by this topological index Z. This index Z is interesting because this is actually a wild charge similar to the wild charge we know from semi-metals. Right? And so this means that if you have a non-zero wild charge, so you have point nodes in an odd parity superconductor that's broken time reversal, then this classification tells you that there's going to be certain Fermi surface arc states associated with that. And that's something you can see experimentally. All right, and so my point with this slide is you can do a topological analysis that only includes the two key symmetries, time reversal inversion, and you find what kind of nodes they allow. But now if you add the other symmetries I mentioned before, you'll get additional possible nodes in practice, like some of the ones I showed you. But these aren't going to be as robust because these symmetries are actually the symmetries that stabilize the superconducting state themselves. Right? And this is, okay, so again, this is to give you a flavor of what's happening now in terms of what we're looking at in terms of superconductivity. And then now I'll come to the final slide. And that is, we've become very interested in Majorana fermions in superconductors. And I really don't have the time to give this field justice. But we know a Majorana fermion is a fermion that's its own antiparticle. And here I'm borrowing an argument from Frank Wilczek's Physics Today article. He pointed out that this is not possible in conventional solid-state physics because particles typically have a definite charge, and going to the antiparticle changes the charge. So the usual solid-state cases, we can't make Majorana fermions because the charge has to be either positive or negative, and that will change undergoing to antiparticle state. However, in a superconductor, I pointed out there is this particle-hole symmetry built into the Hamiltonian, and that's always there. And that means, in fact, that it is possible to create excitations that have zero charge. And so then when you take the antiparticle, it can be its own antiparticle. And you may have heard that these can be useful for quantum computing. And so there's been a massive hunt for looking for these Majorana fermions that can be useful. And here's a result from the Princeton group from 2014. What they did is they took a lead superconductor and they put an iron chain on it. And then they looked at the spectrum through STM to see what the spectrum looked like. And they found that very near the edge here, I think where laser pointers on is dying, but very near the edge, they found there's a state sitting here. And so this is the what am I trying to say? Okay, well, they found that there's a localized state sitting at the end of this, and this localized state was argued to be a Majorana state. And so with that, I'll go to my conclusions, and I think we're finishing essentially just on time. So.